Bismillahirrahmanirrahim. I remind you that the CCR model in multiplayer form for evaluating a DMU named DMUO was named LPO, and its dual was the CCR model in the envelopment form named DLPO. We had two phases to evaluate the DMU, first solving the DLPO and then maximizing summation of the slags in the region of the optimal solutions, in the region that was the set of optimal solutions of the first phase. The optimal solution of the two phases in the phase 2 was named the max slack solution, and when theta star is equal to 1 and R slacks are 0, corresponding to the max slack solution, we say the DMUO is CCR efficient. Based on the max slack efficient solution, the reference was defined, and based on this solution, the CCR projection was also defined, as you can see. It was proved that the improved activity or the CCR projection is CCR efficient. Now we prove a corollary 3.1 that says the point with coordinate x hat O and y hat O defined previously, and with this you can see here, when we say this is efficient, it means that this point is the point on the efficient frontier used to evaluate the performance of DMUO. Note that this is a corollary that is obtained from the previous theorem. Indeed, the CCR projection identify the point either as a positive combination of other DMUs with this relation, and when the theta star is 1 and the slags are 0, this CCR projection is the DMUO. Indeed, by reducing the inputs and increasing the outputs, we can go from DMUO on the efficient to a point on the efficient frontier. Note that this improvement should be achieved by using the max slack solution. If we do this based on another that is not max slack solution, the improved activity is not necessarily CCR efficient. We can see this, for example, by this example that we have 4 DMUs with each with 3 inputs and 1 output. All outputs are equal to 1, are assumed to be equal to 1. This here, the situation for DMUC is obvious. Note that this DMU has two possible slices in the second input x2, sorry, one against A and 0.5 against B. Indeed, we compare C with B, the first and the last inputs are equal, but the second one is half less than, B is half less than the input of the mu C. But for A, the difference between the second input, that is indeed the slack, is 1. So if we choose B as the reference set, as you can compare B with A, you can see that B is not efficient. But if we use the max slack, the solution would be A, that is CCR efficient. Lemma 3.1. For the improved activity or the CCR projection, there exists an optimal solution for the problem LPE, which is dual to DLPE, such that these relations. To prove and indeed to explain the proof of the book, before see the proof in the book, note that DLPE was this model. It was proved that the projection, the CCR projection, is efficient. So the optimal, indeed the max slack optimal solution, which means first minimizing this, and in the second phase maximizing the summation of the slacks, we will obtain the optimal max slack solution as the theta hat is equal to 1 and the slacks are 0. Noting the definition of x hat O and y hat O as before, if you put these values in this model, you can see that putting theta equal to 1, lambda equal to this lambda star, and the slacks 0 is a feasible solution with this model. And since this was the max slack solution, and this solution has the same objective value and the slacks are 0, so this solution is also a max slack optimal solution. Now using the optimal solution, theta equal to 1 and slack 0 and the lambda value is lambda star, we can use the strong complementary slackness to show there exists positive weight with these relations. The last one is the feasible solution of the dual of the DLPE. The second one is obtained by the complementary slackness. You can read the proof now by using the solution indeed with this optimal solution. Note that the model can have, for example, alternative optimal solution, and we may say that this solution, which of course there is a lambda hat, the lambda hat maybe is different from the lambda star. So to be correct the proof in the book, we first should note that this is the optimal solution. Now with this optimal solution we can continue the proof. We use the proof of the book and it is correct now. But we have also prove the theorem in another way. Note that x hat O and y hat O is CCR efficient. We had CCR efficient, two definitions for the CCR efficiency. First, correspond that the envelopment model, another one to the multiplier model, and we proved that these two definitions are equivalent. So now we use the definition that was based on the multiplier form. We know that this DMU, the CCR projection, is CCR efficient if there exists an optimal solution with positive component of weights with the optimal objective value equal to 1. Since every optimal solution is feasible, so we have these. So you had O multiplied by Y is less than or equal to, we had O multiplied by X. This was the last relation that we should prove. Another one was positive. We now should prove that the constraints equivalent to the reference set are in equality form, indeed are binding. To prove this, note that the objective function value is 1, so this was also 1. The minus of these are 0. If we put x hat O and y hat O as we was defined before, this is the inputs of the projection and this the outputs of the projection. We have this relation, and by writing in another way we have this. But note that the lambda j star for j belongs to E or all was strictly positive. From the constraints also we have all of these less than or equal to 0. And we know when the summation of some non-positive values are 0, all of them should be 0. So all of these must be 0. And since the lambda j star is not 0, so these values should be 0 for all the j's. So this shows, this completes the proof. Note that indeed we prove there exists a positive optimal solution, that this the last one you say this is indeed the feasibility of any optimal solution, and we proved the 3.3 by using the relation you see. So we gave two proof for this lemma. one by the proof, indeed by proof of similar to the proof in the book, and another one, as you saw, you can use each of them to prove this lemma. Now we have theorem 3.3 that says the DMUs in EO that was defined before are CCR efficient. For this purpose, we use the lemma 3.1 as it was proved. There exists a positive multiplier that satisfies these relations. Now, to prove for each j DMUJ is efficient, we should use one of the definitions for the CCR efficiency. For example, we use the definition by the envelopment form. Another definition was based on the multiplier form. Here, of course, since these are in multiplier form, the proof based on the multiplier form is easier. So we should prove for each. We use different notation for this. There's no difference if we say DMU JJ belongs to EO or DMU P belongs to EO. For every P in EO, we proved that DMU P is efficient. So we should find an optimal solution with the optimal objective value of 1 and positive weights for each DMUP that P belongs to EO to prove that DMUO is efficient. From the previous lemma, we had this. Since P belongs to EO, we should have this, because we have this for all J that belongs to EO. Now, we define U bar and V bar as this. Note that we have this positive, this one also strictly positive. Indeed, we show these positive ways are the optimal solution for we will show that U bar and V bar are the optimal solution of this model which evaluate DMUP to prove DMUP is CCR efficient. Indeed, we should show the optimal function value is equal to 1. The solution is feasible and the weights are strictly positive. But if we multiply U bar by XP, we have this, and from this relation, these two values are equal So this is equal to 1, and similarly we have v bar xv is equal to 1. This is the objective function value of the model which evaluate the MUP, and this is one of the constraints. For another constraints, note that we have this by putting the values. We have obviously this, but we prove this is less than or equal to 0, and we know this is strictly positive. So we have this less than or equal to 0. So it is there exists positive optimal since we know the value of the max value of this can be 1, so this is optimal. This is one constraint, and these are other constraints of the model. So we prove that there exists positive weights with the optimal value of 1, that with the definition it proves the MUP's CCR efficient. And the theorem 3.4 says any semi-positive combination of DMUs in EO is CCR efficient. To prove, consider a semi-positive combination of DMUs as XC and YC, that CJs are greater than or equal to 0. By using the multiplier of lemma 3.1, we have these relations, and similar to the previous theorem, we can prove that the MUC is efficient. Indeed, by dividing this by this, we can find an optimal solution for the CCR model which evaluate XC and YC with objective function of 1 and positive weight. So it shows that this DMU is CCR efficient.